Welcome to Module 4. So far, we've looked at the markets, the products, and even the derivatives that act like turbochargers. But now we're going to pop the hood and look at the actual engine that makes this whole thing run, the technology.
Yeah, let's stick with that car analogy. Think of modern finance as this incredible high-performance race car. We've talked about the car itself, the fuel, the turbo, but now it's time to get our hands a little dirty. We're diving into the engine room to see the complex system of models, code, and data that actually generates all that power. And we're going to break this engine down into three main parts. First up, we've got the mind. That's the financial models, the theoretical blueprints. Then we have the tools. These are the programming languages that bring those blueprints to life. And finally, we have the memory, the massive databases that remember literally everything. All right, let's start with the mind of this machine. Financial models. Now, these aren't crystal balls that predict the future. Far from it. They're more like an art form, really, the art of simplification. They give us a framework, a theory, for how to price things in a world that's packed with uncertainty. So this brings us to a really fundamental question. How does a bank, or anyone for that matter, figure out what a complex thing like an option is actually worth? You can't just pull a number out of thin air. The answer, of course, is you use a model. So what exactly is a model? Well, the keyword here is simplification. It is a simplified version of the real messy world. It's a mathematical framework that's built on a foundation of very specific assumptions. And its whole purpose is to take all the chaos of the market and boil it down to one single useful number, a price.
And the most famous model of all is Black-Scholes Merton. Now, for its beautiful, elegant math to actually work, it has to assume the world is, well, kind of perfect. It assumes volatility and interest rates are constant, they just never change. It pretends there are no transaction costs or taxes. And maybe the biggest leap of faith, it assumes that stock returns fit perfectly into a neat, tidy bell curve. As you can probably guess, these are some very strong assumptions.
This leads us to a famous saying that just perfectly captures the whole dilemma. All models are wrong, but some are useful. We know the assumptions are flawed, which means technically the model's always wrong, but it is incredibly useful. Why? Because it gives everyone a common starting point, a shared language for pricing things and managing risk, even when everybody in the room knows the map is not the territory. Let's just zero in on one of the biggest assumptions the Black-Scholes model makes. It says that the volatility of a stock, how much it bounces around, is a single constant number for the entire life of an option. It doesn't matter what the price is, it just stays the same. But here's what the actual market data tells us. It shows this beautiful curve known as the Volatility Smile. What this means is that, in reality, volatility is absolutely not constant. It changes depending on the price. The market itself is telling us loud and clear that the model's core assumption is just plain wrong. Okay, here's another huge simplification. Because the model relies on that perfect bell curve, it predicts that huge market crashes, those wild extreme events, are so ridiculously unlikely that they should basically never ever happen. And yet, we all know they do. The real world has what we call fat tails, and that's just a fancy way of saying that extreme events, both crashes and bubbles, happen way more often than the neat little bell curve says they should. For example, the model suggested a crash like the one in 1987 was a once-in-a-billion-years event. And if you want the ultimate example of model failure, look no further than the 2008 financial crisis. The risk models used by all the big banks were built on one critical assumption, that housing markets in, say, Florida and California were not perfectly correlated. The whole idea was that if one went down, the other would be okay. But in 2008, everything went down together. Correlation shot up to 1. The diversification they thought they had just vanished. And the models broke right when they were needed the most. So, if the model is the mind, the big question is, how do we actually make these theories do something? Well, for that, you need tools. And in modern finance, the tools are programming languages. They're what turn all that complex math into code that can actually be executed. And really, two languages rule the quant world. You've got C++. C++ is all about one thing, raw, blinding speed. This is the language of high-frequency trading, where every single millisecond counts. Then you have Python. Python is the modern Swiss Army knife. It's not as fast, but it is incredibly flexible. With amazing tools like Pandas and NumPy, it's become the absolute go-to for data analysis, testing strategies, and building new models quickly. Now, just to give you a feel for it, let's look at a super basic concept in Python. A list is exactly what it sounds like. It's like a shopping list. It's a collection of items in a specific order, and you access them by their position, the first item, the second item, and so on. A dictionary, or dict, on the other hand, is like a real dictionary. You don't ask for the 500th word. You look up a specific key, the word, to get its value, the definition. Simple, but powerful.
So what happens when you have a financial product that is so complex, so exotic, that an elegant, clean model like Black-Scholes just can't handle it? Well, that's when we turn to brute force. We use a technique called the Monte Carlo method, which is a fascinating way of using randomness to find an answer.
So here's how it works, step by step. First, you set up some rules for how a stock price might move around. Then, you tell a computer to simulate thousands or even millions of random possible future paths for that stock. For every single one of those random paths, you figure out what the option's payoff would have been. After you have all those payoffs, you average them all together. And finally, you discount that average value back to today. And voila, that average is your fair price. It's pricing by sheer computational power.
All right, so we've got the mind and we've got the tools. But where does a massive investment bank actually store the data from the millions of trades it does every single day? That brings us to the final piece of our engine, the memory. In this case, the bank's database. And to talk to these gigantic databases, you need a special language. It's called SQL, which stands for Structured Query Language. Honestly, the best analogy I've ever heard is this. If the database is a massive warehouse, SQL is the language you use to tell the forklift robot exactly which box you want it to go find for you. So let's imagine a trader walks up and has a pretty simple everyday question. They just want to know, hey, can you find all the big trades we've done in NVIDIA stock? How do they ask the database to pull that specific information out of a sea of millions of other trades? They do it by writing a query in SQL. Now, this might look a little intimidating if you've never seen it, but it's actually super logical. It almost reads like an English sentence. This is the precise command you'd give the database to answer that trader's question. And let's just break it down. Select asterisk basically means show me everything, all the columns of data. From trades tells it where to look, from the trades table. And where is the magic filter? It says, but only give me the rows that meet these specific conditions. In this case, the asset has to be NVIDIA, and the amount has to be over 1 million. It's that simple. With just a few logical lines, you can pull exactly what you need from terabytes of data in seconds. This is the foundation of everything from risk reports to regulatory filings. And that really brings us full circle. The model is the mind. It gives us the theory. The code is the tool. It brings that theory to life. And the database is the memory. It stores all the results. You can't have one without the others. They all have to work together perfectly to make up that powerful engine that drives modern finance. So we know that today's models work pretty well. 99% of the time, when things are normal. But we also know they fail during times of crisis because they just can't account for those fat tails. And that leaves us with a really big, kind of scary final thought. What impossible event, what new black swan are today's models completely blind to right now?